Welcome back to the Packet Lab. Today we're going to take a look at another of the frame relay basic configurations, and in today's lesson we're going to take a look at configuring a basic hub and spoke topology. Okay, so if you tuned in for the frame relay basic point-to-point configuration lesson, a lot of this is going to be review. Bear with me, it does get, well, if not interesting, at least different when we get into the nuts and bolts of hub and spoke configuration. So anyways, the reason I have these simple configuration lessons is to A, break up the monotony of listening to me drone on and on about theory, and then B, to expose you to a baseline configuration, because especially in the case of hub and spoke configuration, what we go through today is not going to be your quote-unquote optimized configuration. It's not what you're going to actually encounter or design in the wild. And it's good to take a look at these basic configurations. And especially in the case of frame relay hub and spoke, there are some interesting aspects to this that you will design around when you're actually rolling this out into a real network. And it's good to take a look at this baseline configuration so that you can understand some of those complications and why your configuration needs to address these. Anyways, let's get started here. So as I mentioned in the topologies and design lesson, the hub and spoke network design really highlights some of the benefits of frame relay. Hub and spoke is basically a star topology where all traffic will traverse the hub. So you'll have a hub, which is generally going to be like a corporate headquarters, and then the spokes will be your remote offices. So to save money on equipment and circuits, you just have a connection from each spoke to the hub, and then the traffic from spoke to spoke will traverse the hub. So this does have some cost savings in circuits and equipment, and it's also kind of beneficial with frame relay because you can set different bandwidths on the spokes. Of course, the obvious caveat with this is that you do have a single point of failure. If your hub is down, then your spokes can't talk to each other. So here's a simple frame relay hub and spoke design that we're going to use today. We're going to have 3 routers. R1 will be our hub, R2 and R3 will be our spokes. So you can see here that each of the spokes only has a single connection, and that is a virtual circuit going to the hub. So if you're going to communicate from R2 to R3, you have to send that traffic to R1 first, and then R1 will send it back out to R3. So again, this saves on money and equipment costs, but it can be detrimental as far as a single point of failure up here on R1. And sometimes if your spokes are geographically close, you can see if this is San Diego and LA and this is New York, you're sending traffic all the way up to New York and then back down to LA. So that can induce significant delay. So in that case, you'd probably want a modified hub and spoke and just have a direct connection here. But those are all design considerations that you might run into when you're actually rolling this out in the real world. For those of you who watched the frame relay point-to-point configuration video, a lot of this will be reviewed. Bear with me. First thing you're going to want to do is you're going to want to set the encapsulation type on your interface to frame relay. By default, serial interfaces on a Cisco device are going to be set to HDLC. And you can verify that with a show interfaces and then specify your serial interface. And here you can see the encapsulation is HDLC. The command to set the encapsulation to frame relay is very simple. It's simply encapsulation frame relay. Make a note here that I do like to shut down the interface prior to making any encapsulation changes. I actually like to shut down the interface when I'm making almost any change. The reason is that you're not going to benefit by keeping it up. That's what she said. You're not going to benefit by keeping that interface up, because if you are changing encapsulation, previous encapsulation is going to fail. So if you had this set to HDLC and you had traffic running through there, the second that you set it to frame relay, that HDLC traffic is going to fail. So you might as well shut it down. Technically, you can keep the interface open and do this configuration, but you're just inviting Cisco iOS goofiness to come and bite you in the butt. So shut it down. So as soon as you set the encapsulation to frame relay, you will see the results of that on your interface. And you can see here we're still in configuration mode. The interface is still administratively shut down, so we haven't issued the no shut command to bring it back up, and I'm issuing the show interfaces 00/0. You can see now instead of HDLC, our encapsulation has been set to frame relay. You'll also see some additional information here, and this is the LMI information, which is unique to frame relay. You won't see this with HDLC or PPP because it doesn't exist with those protocols. The LMI is your local management interface, and if you harken back to our first lesson, that's the communications between your router, which is going to be considered the DTE device, and the frame relay switch, which is going to be the DCE device. So this is the way that it knows that it's there. It's a keep alive mechanism. It also allows the frame relay switch to advertise DLCs to your DTE/router. So it's going to say I've got DLC 101, 102 available. So that's how you're able to see which local DLCIs are available. The default LMI type on a Cisco device is going to be Cisco. Two important things about that. While that statement is technically true, it's not really operationally true, because although the default LMI type is going to be Cisco, actually by default Cisco uses this feature called LMI AutoSense. So there are three different types of LMI. There's Cisco, there's ANSI, and there's Q933A. Anyways, when you bring this interface up, when you do the no shut, the interface is going to send out one of each of those types. It's going to send out those three, and then the switch is going to receive these. Well, it's only going to respond to the one, actually the ones. We'll get into that in a different lesson on LMI. Don't want to cloud the waters here. Let's just assume it only speaks one form of LMI. So it's only going to respond to the LMI type that it actually is configured for. So let's say in this case it's ANSI. It's going to get the Cisco one and be like, I don't know what the hell you're talking about. It's going to get the 933A one. It's going to say, I still don't know what you're talking about. Then let's get the ANSI and say, hey, that's the language that I speak, and it will respond to that. The Cisco router will get that response and be like, oh, hey, you know what? This guy speaks ANSI. Let me go ahead and set this to ANSI. I said there was 2 points. I don't want to lose the second point. The second point is that Cisco LMI is not proprietary. It's not Cisco proprietary. It's actually the LMI type that was created by the Gang of Four, which included Cisco, Nortel, DEC. I can't remember the other one. Anyways, you can have a non-Cisco switch and it will be able to speak Cisco LMI type. So don't get mixed up with that. 99% of the time when you see Cisco, it is proprietary. In this case, it is not. And you can see here we are the DTE. The frame relay switch would be the DCE. Alright, so once you've got your encapsulation set, there are a couple of additional options you may need configured depending upon your network. You may need to set the LMI type to match that of the frame relay switch. Not really such a big deal anymore, because frame relay on Cisco devices will use LMI AutoSense. I just kind of described that feature. It's going to send out one of each of these different types, and that's going to set the interface to use whichever type the frame relay switch responds to, because that's what it speaks. So a lot of times you're not going to have to set this, but just know that if you do need to set it, for troubleshooting, or say that they have some crazy ass switch that doesn't want to play with Cisco LMI AutoSense, you can manually set that. The second one is probably more important, because there's actually two different types of frame relay encapsulation. There's Cisco and there's IETF. Now, when I talked about Cisco LMI type and I said that that was not Cisco proprietary, that is not the case with the frame relay encapsulation. That is Cisco proprietary. Before I go into that, let me jump back to that network diagram real quick. Okay, so here's our network. It said LMI exists between the DTE and the DC device, and in this case your routers are all going to be DTE devices, and this cloud here you're going to actually connect to a frame relay switch on each of these connections, and those are going to be the DCE devices. So LMI is here, communicating on each of these devices. You're communicating to the cloud. Now, frame relay encapsulation is an end-to-end connection. So while your LMI can come up, if you have set your frame relay encapsulation to Cisco, then you better hope that this guy on the other end is set his frame relay encapsulation to Cisco as well. Now, if you work in a perfect network like I do, where all the equipment is Cisco, then you're golden, because by default Cisco devices are going to use Cisco frame relay encapsulation. So if these are all Cisco devices, you shouldn't have to configure anything. They will be able to speak to each other with the frame relay encapsulation type of Cisco. Now, if for whatever reason you lose your goddamn mind and you'll get a Juniper router up here, say for R1, your end-to-end communication will most likely need to be the industry standard, which is IETF. So at that case, you would set on your spokes frame relay encapsulation space IETF, so that you can talk to your godforsaken Juniper router up here. So just keep that in mind. The LMI is just from here to the frame relay switch, where frame relay encapsulation is end-to-end, and you can actually set the frame relay encapsulation to a default. You could set it on a virtual circuit by virtual circuit basis by specifying it for each DLCI. So you could have this be a Juniper device, both of these be Cisco, and just this connection be set up to use IETF. Anyways, let's get back into this. So like I said, you can set the encapsulation type by just typing encapsulation frame relay, and then if you hit enter, you're going to be using Cisco. If you want to use IETF, you have to go 4 letters further and type in IETF to set that. And this will probably be something that you would more likely run into in the wild than having to set the LMI type. Okay, this next step is to disable frame relay Inverse-ARP. There's going to be a separate lesson on frame relay Inverse-ARP. This is optional. Today it's not going to be, it's going to be mandatory. We're not going to say much more about this other than in this lab today we're going to go ahead and disable that, and the way you do that is with the no frame relay Inverse-ARP command. And then finally you're going to want to apply your layer 3 address to the interface. We're going to be using IP, so you just use the IP address command with the IP address and then the subnet mask. Alright, and this final step is the step that confuses a lot of people because it is pretty unique to frame relay. Unlike Ethernet, frame relay does not have a true address resolution protocol, or ARP. We disabled the pseudo ARP feature when we disabled frame relay inverse ARP in the last step. So what that means is we need to manually map layer 3 addresses to the layer 2 addresses. In this case it's going to be IP addresses acting as our layer 3 address, and our layer 2 address will be the frame relay DLCI. And the command structure for that is frame relay map, and then the next bit you choose the layer 3 protocol. You can choose IP, IPX, AppleTalk, DECnet. There's a whole bunch of them. We're sticking with IP, so frame relay map IP. And here's the part where most people stumble. You're going to be mapping the remote IP address. So in this case we're on R1 and we're creating a layer 3 to layer 2 mapping for our connection to R2. So we're going to use R2's IP address, which is going to be the .2 address, and then we're going to map that to the local DLCI. So remote IP to local DLCI, and we'll discuss the broadcast command in just a bit here. First, let's jump back to our map. Okay, so what we're doing here is we're going from R1 to R2, and we need to create the mapping. So it's frame relay map IP because we're running IP, and then we're going to say to get to 10.1.123.2, I need you to go out DLCI. And this is where a lot of people get confused, because with Ethernet, if you were to have this be an Ethernet network, IP address is mapped to the remote node's MAC address, would be its layer 2. So if you did a show IP ARP with this IP address, this .2 IP address, it would be mapped to R2's MAC address. Frame relay is a little different beast here, because what you're telling the router is that to reach this next hop IP address of 10.1.123.2, I need you to go out this local DLCI, because if you're on R1, it has two choices. It can send traffic out DLCI 102 or DLCI 103. Since 102 goes to R2, you're going to say frame relay map IP, because we're running IP, 10.1.123.2, because that's the remote IP address, or you can think about the next hop IP address, and then you're going to say 102 for the local DLCI. And so that's saying to R1, it's like anytime you need to reach this IP address, go out this frame relay DLCI. Okay, here's that frame relay map statement broken down a little bit here. So it's frame relay map and then IP, because we're running IP as our layer 3 protocol, and then the remote, remember remote layer 3 IP address, which is going to be 10.1.12 in this case, and then the local DLCI. This is the part where most people get tripped up. They either map the local IP address. Usually it's not the IP address that throws them off. It's usually mapping it to the remote DLCI, because they start thinking stuff like Ethernet. And I mean, that logically that makes sense. You would think that that's what you would do, but you have to remember that DLCIs are locally significant only. So if you remember remote IP address, local DLCI, most of the time you'll be golden. And here's the broadcast statement. So frame relay does not pass on broadcast by default. So by adding this broadcast statement, you're enabling frame relay broadcast, kinda. You'll notice that it's called pseudo broadcast support. What it's doing is it's taking that broadcast address and it's changing it to a unicast address, and we'll go through this in a lot more detail later, but generally you're going to want this, because especially if you're running a routing protocol that uses broadcast addresses like, you know, RIP or any of that stuff, you're going to want to have this keyword on your frame relay map statement. But like I said, we'll go through that in a lot more detail in a later lesson.